from yesterday. Anything you would like to be further clarified or discussed? No? Good. So then we go on. And I think we left, what did we leave actually? Oh yeah, these are skipped yesterday, maybe I should. It's again a little bit mathematical, but there is one point, important one, relatively important point I want to make. Again, related to the expansion of the distribution function in the big polynomial, and particularly the form that this expansion takes when you expand on the lattice. Okay? Remember, there is always this distinction. You have a limit, we continue kinetic theory, well known for half a century or more. And the question is, how do you translate the same language into the lattice? Sometimes it's trivial, most times it is. But essentially, the point I want to make here is rather, I would say, general. So I told you yesterday that there are three Hermite polynomials, there are three levels of the polynomials. The skyscraper I was describing. So ground 0, 1, and 2 actually. Here we have H0, which is 1. Here we have H1, which is in fact three polynomials because it's a vector, so that would be 2, 3, 0, 1, 2, 3. And then H2, which is a tensor, because basically it's a dyadic, is eternal basically, for the number of dimensions times the identity. So this is the unit matrix, this is the dyadic. Again, just to make sure we understand each other, I think you know what the dyadic is, but this is dx dx, dx dy, dx dz, 3 by 3. Okay? Okay? So this is, in fact, since it's a symmetric, it's 6 independent components. So in the end, in 3 dimensions, we have 1, 3, and 6, which is generally 1d, because this is a vector, in d dimension, d times d plus 1 over 2, which makes 6 if d is 3. So, as you see, here my life is easy. I've just taken I means that I'm in the lattice, and H0i is just H0 and just the very same. Right? No question. Same game here. I say that H1a, A again labels x, y, z, so we have 3 of them, is a discrete vector CIA. And again, just to fix the notation, CIA is then B2Q9 setting. It will be C1, and CIA is C1x, C1y, C1z. Okay? That's what they mean. Of course, you cannot expand this notation with PowerPoint. It would be filling up too many pages. And here we have the tensor HAIB, and again, my life is very easy because it's just the literal transcription of the lattice of the continuum. So here I can really say V equals CI, nothing happens, and I have 10 of them. Now I give you a little assignment. You want to run your code using this lattice, which you know by now is the D3Q19. There are 18 connections plus the rest particle. And since we have an index I here on the distribution function, we will have 19 of them, right? Now the question is, if I expand this distribution function, okay, as I said yesterday, this is the basis, and there should be, in fact, 19 of these components and 19 fields. Okay? Because, I mean, if I project Fi, so I have the information, the space-time dependency of Fi, in fact, is contained in its coefficients. So rho is the fluid density, rho of xt, J is the fluid current, function of xt, P is basically the momentum flux tensor, function of xt. So you see there has to be a balance between the representation of the discrete distribution function, which is f, and the representation in the fluid variables, which is rho, j, p, blah, 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 blah. So it's just like having, again, that reminds much of quantum mechanics. So I have a vector Fi, okay, and I runs from 0 to 18 in this case. So I'm spanning a space which contains 18 dimensions. Okay, I could say that F is a vector in this space, F1 or F0 up to F18. Okay? This codes the state of my system, side by side, time by time. But in the fluid representation, I have something else. In the fluid representation, I have fields, which is the coefficient of this expansion. Okay? And they have to match. So I will have rho, I will have J, Jx, Jy, Jz. I will have P, Xx up to P, Zz. That makes 6, that makes 3, and that makes 1. There has to be more, right? Otherwise the transformation would be somehow non-one-to-one. And this more, I'm going on here. I'm writing, okay, I know from the mid theory that I have a mid polynomial number 3. This starts to be a little bit messy because I have 3 times 4 times 5. So this makes how much? I don't know, but certainly if B is equal to 3, I'm not matching the length population. Okay. So the point I want to make is that we need to choose certain lattices, and we are constrained by the symmetries we have been discussing in the last 3 days. But there is no guarantee. In fact, in general, the number of links or the number of discrete populations which are dictated by the lattice will not match the limit expansion. So there will be really structural mismatch between these two representations. Okay? Which means that at some point, and then you see that pretty clearly from the math, because now I give you a specific example. Consider this lattice again, and I told you yesterday that this lattice is just comes from the D3Q27, so the one with all the, including the 8 corners, just by taking the generator -1, 0, +1, cube. Okay? So -1, 0, 1, -1, 0, 1, -1, 0, 1 generates the 27 nodes of the D3Q27. And then for some magic, we can do with less with that, but let's stay with the D3Q27. Now, when we go to this polynomial, I told you yesterday that this is a tensor polynomial of order 3. Now, in fact, populating this floor, this skyscraper, this is infinity. So this is where density lives, but in fact, there is also current, and they are connected. Here there is the momentum flux, P, and here there is the energy or heat flux, if you want. It's just like in the column, so to say. Okay, so this is order 3. Now look at this expression. If I work on this lattice, the lattice analog of V cube is dominant, because Ci cube is just Ci. -1 cube is just -1. 0 cube is 0, and 1 cube is 1. So there is a linear dependence in this. This structure is not supporting independent third-order unit polynomials. Some of them might be independent, but not all of them. Okay? Same thing goes for the next orders. Right? Ci4 is just photocopy of Ci squared. So that means that this structure does not provide enough freedom to fill the bill at the level of the heat flux. You see that very transparent. Okay? So what do we do? Well, of course there are ways around, but I just wanted to make again the point why describing heat flux becomes complicated. There is no way of describing this with this lattice. I mean, you can compute this quantity on this lattice, it will be bogus. It might sometimes be useful just for numerical purposes, but physics, 0, -1, okay? So that explains you why, indeed, if you want to do physics at this level, there is no way other than going to higher order lattices. And So we realized that in the early days, but in a different way, much more obscure. The point I want to make is that then you have to decide what you're going to put here. And here I must say I see a weakness of the Lattice Boltzmann approach because this is to a certain extent arbitrary. Here I can no longer play the nice game V equals Ci, no more. I have to choose, and very often I can tell you this weird thing happens. Sometimes, so you stop at the level, sometimes you have to pick up something from the next floor. Well, it's not obvious. I think nobody knows, in fact, what is the optimal representation at the level of the quotation mark. In the back then, we call this ghost fields. And I think the name is appropriate. In fact, it's become rather popular. We call them ghost because they do not emerge at the level of hydrodynamics. I mean, these quantities are not supposed to be there when you watch your turbulent flow, when you watch your flow bubble. They have no hydrodynamic content. Okay? So if you want, if you do an isothermal flow, that's what you want to see. I mean, all this should be hidden, should not, is not observable, so to say, at the hydrodynamic level. Nevertheless, these guys have to be there, because if they are not there, then you would not have the right crystallographic symmetry. So this is information is like dark matter, so to say. It has to be there, but you don't see it. You don't want to see it, actually. So do you get the point? Not really. I see that your faces are not very happy. Yeah, please ask questions.
How many of them should be there?
Oh, I mean, you should know. I should. We have, now what did I have? We have 19 here. I say that 10 are clean. Okay? Now I am embarrassed because I cannot tell you by heart how many I can pick up from here with physical meaning. I think very, very few, because this really spoils the game. But let's say that I cannot pick up anything here. So all these vectors are in fact linear combination of this, which I think is true. It's lattice. Then here I will have 1, 3, 10, and I have 18. So I have to pick up, in fact 19 because we have the rest. So I have 9 ghosts.
But the 19 comes from the fact that I need the crystallographic symmetry.
That's right.
And that comes from the fact that I need to actually represent the tensor on a grid like this.
That's right.
So there should be a relation which...
Well, frankly speaking, I do not quite understand deeply. Well, let's say. I mean, these are two different representations of the same physics. It reminds me, but it's, you have to be careful with this comparison. When you have, again, in quantum mechanics, you have the representation where you have your wave function and you expand on a given basis, but you could do that somehow in Fourier space as well. Okay? So we are very familiar with different representation of the same physics, but there has to be a match between the number of degrees of freedom. Degrees of freedom cannot just evaporate on air. Here again, there has to be a match, because if I expand this distribution function in the mid basis, and the coefficient are the hydrodynamic quantities, and there has to be as many fields. This is a field itself. F sub I is a field. I just label as a discrete index because I can identify this field with the probability for a particle to be moving there, whereas rho, which is again another field, is just the sum of all these probabilities attached to this lattice, but they are both fields. So there have to be as many fields in one representation. I would call this a velocity representation, and this is the hydrodynamic representation. Okay? All I'm saying is that since in this representation you are just ruled by the crystallographic symmetries, at some point they don't go with the Hermite representation. I don't know. The Hermite representation is again a symmetry in some other space, probably. I really don't know.
Well, there are two issues. You choose the basis to span the space,
Right,
And
it's
then-
Hilbert
Yeah,
space,
and
right?
then by, you handcuff yourself to the lattice, that tells you how many ghost fields you have. You change the lattice, you change the ghost.
You
field.
change the lattice, you change the ghost, absolutely. Absolutely. So, but I think a myth is,
So do you necessarily need this symmetry
Which
to
one?
preserve isotropy of the system, of the physics? Do you need it? No, because otherwise you could just choose arbitrarily numbers of vectors or grids.
no, I mean, that's point number one, I mean, you have to be strict. Well, we were discussing yesterday, some of you about being a little bit more liberal on the quasi-crystal.
Yeah.
But this game is very dictatorial. I mean, the symmetries have to be there and there is no, cannot escape that. It's very strict. As John pointed out, I changed the lattice, I changed the ghost, and I changed the performance of my code. Not the performance, the stability. So just to say that this is typical of Lattice Boltzmann, so somehow you have more freedom, but it's also, freedom goes with ambiguity, so you can do better things, you can do worse things, right, as usual. And so we have our own recipes on how to construct the ghost space, but this is not unique. And I would say that nobody really knows what the best ghost representation is. So you should be prepared to that. You would not bother about that unless you really have to do thermal flow, right? For the non-thermal thing is plain. Okay? But the day you start to deal with thermal flow, or I would say also for reasons of numerical stability or isothermal flows, so no physics, but this piece of the tower can have an effect when you really push the resolution and the viscosity down. That can have an effect on the performance of the code. This is highly technical. But if you get wet with this calculation, then you should know. That's nothing to be here in a general class. Okay, but I wanted to make you aware of this mismatch, the structural mismatch between the Hermite space and the Hilbert space. Okay? We will be using this pretty much possibly today, and tomorrow as well, because this expansion, as I was saying yesterday, is very useful the day you want to construct generalized hydrodynamic equation. As I said, I eat my words back when I saw the Hermite paper. I said, so what? That's trivial. No. It's really useful to have this.
How does the Boussinesq approximation change the picture? I mean, you said one need not bother about the higher things if one uses a Boussinesq approximation when solving for.
The Boussinesq approximation is sweet to us because we don't need to bother about that. We do this, and then we eventually solve for the temperature either with another to find a difference. So you don't need to represent the thermal fluid all in Boltzmann. Many people are very happy with using Boltzmann up to here, and doing the thermal transport is a different approach. In the early day, we did really fancy things. It's crazy, in fact. I tell you just for fun. When you start, you remember what I told you, in the lattice gas, in fact, these links carry two components because they come from the fourth dimension. So you should see this as a degenerate link with two particles, say with velocity plus and minus 1 along the fourth dimension. It turns out that the sum of these 6 links along the fourth dimension is a passive scalar. And so we use that to model Boussinesq. Boussinesq is a passive scalar, So to us, the Boussinesq temperature was contained in the fourth, was the current along the fourth dimension. It looks crazy, but it really works. But that was really back then, just 8, 9, 9, something like that. We have a paper I'm very proud of, and not very well known, where this trick really works pretty well. But in general, what I'm saying is that Boussinesq doesn't need to be considered. So here somehow you have to fill your space in a way which is reasonable and in a way which is not really disturbing your physics too much. Okay? And this lattice is okay, no question, but different groups have different representations. No big deal in general. Okay? But we just wanted to make it aware. So having said this, I think that is, okay, so as I said, there are many lattices. And now we move, if there are no further questions, we move very shortly on this multiple relaxation time, which really is a refined, optimized version of the Lattice Boltzmann as it was born, because Lattice Boltzmann was born in matrix form, by now you know very well, and many people just don't know or forget or want to forget, I don't know, especially, but anyhow. But people should know the fact that I wouldn't say that this is old wine in a new bottle, that would be too loud, because there is some interesting development to that. But people think, most people now, they think that the Lattice Boltzmann was born in BGK form, and it is not at all. Okay, so again, I want to be lightweight, but essentially the idea is the following. This is again a little bit mathematical, but you can think, in fact, of this distribution function vector, so to say, in kinetic space, as made up of three major components. There is one component which projects on the conserved quantities, and I will be explicit what I mean by this and this. If you stop here, you're just projecting upon density and current, which is the conserved quantity. They are associated with mass conservation and momentum. Okay? So this would be the first component out of three. Then there is and this is associated, in fact, with quantities which do not change, which do not carry any contribution from non-equilibrium. If I compute the density with the equilibrium distribution function or with the actual distribution function, I see no difference, because the non-equilibrium does not contribute to the conserved quantity. So rho and rho equilibrium are the same, and J and J equilibrium are the same, because they are conserved. Then I go to the next piece, and this piece is what usually one calls the transport component, because this piece, I was telling you yesterday, has contribution by both equilibrium and non-equilibrium. So we are talking floor number 2. You remember I told you that the pressure tensor PAB contains advection, U grad U, and contains pressure, P, meter Pascal. Okay? And ideal gas, this is the pressure. But, and so this is the equilibrium part. But there is also non-equilibrium part, which is basically rho grad A U B, something like that. Okay? So the transport component is collect contribution by both equilibrium and non-equilibrium. And then comes the ghost part. When I say ghost, I mean I refer to non-thermal flows. Otherwise, this would be physical. Okay? So I'm referring to athermal flows or isothermal flows, as you like better. I think athermal is more correct than isothermal. And this part only collects contribution from non-equilibrium. Okay? So this is the most ephemeral. This is the connector between non-equilibrium and equilibrium. The transport takes place, dissipation is here. And this is the equilibrium part. This is the conservative pattern. Okay? In BGK, all of these guys relax to their equilibrium. They don't relax because they are conserved, but you could say they relax with the time scale 0. Okay? With the same omega, which is not right. So people, I mean, this we know, everybody knew from scratch. This is not right, it was just convenient. But then people realized that by giving a different relaxation time of frequency to the conserved time sector, this is 0, of course, because they are conserved. So you have a spectrum, and in BGK, everybody gets the same omega, and omega has to be between 0 and 2 for numerical stability. Never mind. I will tell you later. So, to the very least, you can now recognize that there should be at least 3 tactile eigenvalues within the strip 0, 2. Conserved mode, of course, have to have 0 eigenvalue. Transfer mode have to have some omega, which is between 0 and 2, and that will dictate the viscosity. And the ghost mode, in the early days, we tried to kill the ghost mode as fast as possible, but again, you have some freedom there. And again, nobody really knows what the relaxation of the ghost mode should be. In principle, you would like to get rid of them as fast as possible, but people show that this is not the best policy. But again, this is highly technical, and I would not confuse you with this technicality. The point I want you to recognize is that there are 3 qualitatively different components in this vector: conserved, transition, non-equilibrium. This has to go, you have to see that. This is the situation, and this is the conservative value. And it is only natural to give different eigenvalues to them. And that is, I had this picture, but that's just another way of rewriting the same thing in a simpler Lattice. This is it. Can you help me with, just as an exercise, with the count? Kinetic degrees of freedom versus hydrodynamic in the TQ9. So how many hydro do we have here? Let's do it together. So what do I have? Here we have how many kinetic components? I'm sorry, you just chose the wrong place. Right, very good. Right. So now let's construct the list of the moments, the hydrodynamic fields. What do we have there? First field. Around 0. Who lives there? Yes. Second floor number 1. Who lives there? Current and how many? No. Let me play. How many currents do we have? How many components do we have? 2. We have Jx and Jy. So that makes 3. Then it gets a little bit more involved. We have a symmetric tensor to the how many independent components? I think it's 4. Isn't it? 1, 2, 3. Oh, sorry. I have to do the exercise myself. 5. But this tensor has to be 0 trace, so they are in fact 5. That doesn't, no, it's not enough money, so let me do it myself. Rho, Jx, Jy, that makes 3. Then we have Pxx, Px. Ah, no, but this is 2 dimensions, sorry. Yeah, very bad. Yeah? So it's symmetric, so we have 3. So we have 6 hydrofields, 9 kinetic, and how many ghosts? 3. Now, from this lattice, in fact, it turns out that the ghost dynamic can be cast in a very symmetric form, very beautiful, but as far as I can say, useless, because the ghost field can be identified with some themselves with some antisymmetric density and current. So there is a structure in this lattice which is peculiar, but I wouldn't bother with that. But all I want to do is just to write down explicitly the Hermite expansion for each of these subsectors. And now you recognize it again. So the conserved sector is just density, Hermite 0, current Hermite 1 along x, current along y. The transport component of this Qi I have not defined. This Qi is just the mid numbers too. Qi AB is CIA, CIB minus C squared delta AB, so it's H2. So you have the H2XX, H2XY, H2YY, and then you have the famous ghost. And I know how to construct the Rontil, the Jtil, but I will not bother that. All I want to say that for the case of the TQ9, this representation is pretty clean, but in 3 dimensions, of course, there is more freedom, so things become more and more. The important point is that the following. So the eigenvalue here is 0 because Rho and J do not relax. They are the same equilibrium, non-equilibrium. one useful thing you can do, the typical useful thing you can do in the multi-time relaxation, that here you would give different relaxation time. If you want, for instance, an anisotropy in your relaxation process, you could choose different omegas for XX, YY, and XY. And by doing that, that turns out to have an effect. Even if you're running an isotropic flow, actually, so that XX and YY are the same, the fact that you have two relaxation values instead of one means that you have some bulk viscosity, which is zero in the BGK. BGK, you don't have any viscosity for these bonds, only have viscosity, shear viscosity. And that has an effect on the stability of the system. And it's a serious thing. Again, when you go to high Reynolds number, typically if you don't dissipate this node grow up, especially if the velocity goes above 1.2, and they can really ruin your simulation. By playing with these, people have shown that indeed you can tame this instability. So that is a serious contribution. Again, in my opinion, it was really overhailed, but it's not that. Not at all. This I know what to say. Yeah, just if you want to, just let me give you again on the flavor. The point is the following. There is a disadvantage in going to the, so this is the mid representation. Okay? So I'm expanding, again, these are the moments, so density, current, etc., and these are the distribution factors. From the coding point of view, this representation is perfect for the streaming because, as we recognized in previous lectures, I mean, this just means that F sub I will just move to the next near location, and that will be this is exactly correct. So the streaming, we really want to move this representation. But the collision operator, in fact, takes this form in the multi-relaxation time context because this is a matrix. Okay? And this should be omega ij, fj equilibrium minus fj, which is a little bit more cumbersome. Okay? So what people did to be smart, they said, no, let's do the collision in the mid basis and the streaming in the kinetic basis. I will spare you the algebra, but you can guess that there is a transformation matrix in between. People do that in the pseudospectral code, right? Sometimes, or in quantum mechanics. I mean, kinetic energy, you're doing P representation, and potential interaction, you're doing space representation. You do the move in the representation where your operator is diagonal. So there is a smart piece of work, mainly by people again in France, Dominique Dumier, and in Germany. They optimized, that's really what they did, the transformation matrix between this representation and this representation, so that in the code, both streaming and collision are done with diagonal matrices. So you understand that it is more cumbersome than just being plain GK. But in the end, if you do the effort, the performance toll that you have to pay is rather marginal. In 2 dimensions, if I go to 19, of course, the transformation matrix is 19 by 19 with many symmetries, but nevertheless, you have to do every lattice size every time step. So there is a price to pay for stabilizing your code. But in my view, whenever you can gain just a little bit of epsilonics into the Reynolds number that you can run, this, since the compute power goes with Reynolds power 4, you always win. And these things are marginal. If this wins you a factor 2 in Reynolds, you win a factor 16 in 3D. And certainly this transformation of between the two representations will not take you 16 times more. So it's a nice playground to optimize your code. The real weak point of this, in my opinion, is that this optimization is not universal. And that is where I'm critical of the literature, because they present you very complicated computation in 3D, high Reynolds number, and they tell you, okay, omega x and omega y have to be 1.233, etc., etc. But if now you change your setup, you have no guarantee that the same omega will do the job. I realize that people would, I mean, it's not nice for me to say that without telling these people in the audience because they would immediately react, but it is my own experience with people in Rome. I know it's a small company actually, so they really need to do the computation. In fact, they want to win Ferrari. So it's, that makes things exciting, but, and they experimented with that, and for sure, they get better results with this than with GK, but each time you have to refine tune your thing.
So what would be your suggestion for what would be the best approach for one IRS?
The best approach for an IRS, you have just to be patient 10 minutes, and you will know, because it's the entropic method that I'm going to discuss. But these things is effective, can be effective. All I'm saying is that I don't see enough universality. The beauty of the GK is that is canned. You get the equilibrium, you choose omega, you go. That's why everybody likes it. But if you have to optimize, then you have to get what different things. I would recommend entropic rather than this, and many people don't like me because of this, some people. So there is some friction in that
You
respect.
tell us what.
I will tell you why, but I really am not the kind of guy who wants to tell you should do that. You do what you figure out by yourself. I tell you what my opinion is, I can always be proven wrong. This I'm very aware of. Yes.
When you say change your setup, what do you change?
Well, I mean that you do backward facing step instead of flow past the cube.
Oh, you mean you just change the geometry and it
The
changes? I see.
You know, this is a trick. When I tell you, it's a smart trick, it's still a trick. There's no fundamental physics behind the fact. Well, yes, there is physics. By using two omegas, I'm generating bulk viscosity, okay? So you would say that's a physical effect. And I know that, I mean, not me, everybody knows that these modes can destroy your simulation on a purely numerical basis. Because these modes should not be there in an incompressible flow. Lattice Boltzmann always has some little bit of compressibility, right?
So in some sense, when you are increasing your Reynolds number,
Yes?
you are also increasing your Mach number.
Right, exactly.
So you can't really control the fraction of incompressibility.
It is like that. Let me amend just slightly. With Lattice Boltzmann, we have never exactly compression. I should have stressed that more. We never had div u equals 0 exactly, no. Because we evolved the pressure field. Okay? So it's just like having, I showed you yesterday, you have an evolution equation for the pressure. So that reminds it's a weakly incompressible map. Okay? So we always have some weak compressibility, but that has to remain small. Because of what I told you yesterday,
Exactly.
otherwise the local
Yes.
equilibrium would be negative. Okay? So this weak compressibility is healthy, but if it grows too much, and just to have some bulk viscosity, just to keep this effect under control.
But if one is increasing Reynolds number to a high value, can the effect of the increase, can't it be observed in the Knudsen number and the Mach number still be
Well,
kept
now
in-
you're
kept in a
taking
check?
me into, yes, let's say, it's very hard for me to say general things on here because really here it's a typical territory that you don't know to do it yourself. But basically the trade-off is always the same. You know that you can always write, I think this is called the Kalman relation, you know that. Everybody's familiar with that? It's trivial, it's just u L over viscosity, and you write u over sound speed, okay? And then you put, how do you do that? Mach, yes. No, I'm confused. And then I put LCS, and u, so this is Mach, this is Reynolds, and this is Knudsen mean free path, so this is one of the Knudsen. Yeah, that's good. So, I want Knudsen to be small because otherwise I'm far off equilibrium long and I want want Reynolds to be I because I want to be turbulent, and I want Mach to be small because I'm lattice Boltzmann. Okay? One way of increasing Reynolds given Mach is to go low in Nutzer, right? That's the typical way. If, on the other hand, you're trying to do this is dangerous. This is compressibility. So if you, for some reason locally, your flow develops some large velocity, then you're in trouble. That is the kind of problem which very often spoils your scenario. And this viscosity helps control this. Okay? So it's almost time to take a break. It is time to take a break because then I would, or either you ask me a question, or you just start with the Entropic, and unfortunately I couldn't find any picture of Santos on Firmar either.
Even the website doesn't have one.
I found one of a little kid which looks like his son.
Yes, it's on Facebook, I guess.
Yeah, but his son is not named Santos, so I don't, he must think so. So there should be a separate picture here, but I'm not responsible for it. So this is Ilya Karlin, who is now back in Zurich, and I think he really should be credited for developing this, together with Santos and the student in ETA. But and in fact, I was again lucky enough that he visited me. He was just on his way out of Russia back in 1998, and he visited me with a fellowship. And it was really lucky for me because when I told him about, was basically an expert in entropy, unionization, this kind of thing, in the Russian school. And as soon as I exposed him to our story, he immediately realized how to transfer his knowledge into our field, and I think that really turned out to be a very successful development. So let me begin, and then I will take a break in maybe 10 minutes or so. So I told you yesterday or the day before that when we played the reverse engineering trick, which is to say design Lattice Boltzmann out of top-down, out of general symmetry of hydrodynamics, instead of deriving it from lattice gas, we were very lucky because the thing worked in a territory where there was no guarantee that it would work. Why? We did a crime, and the crime is rather clear. In the language of statistical mechanics, it's called realizability. Okay? Realizability means that if I have my microscopic model, okay, let's say that we have meso, mu, micro, small m, and macro. Okay? It's a general thing, not only that. So now, if you take, say, Newton mechanics, you go to real Boltzmann, you go to Navier-Stokes, here you have a rope where you are guaranteed that you're doing something which is physically sensible. Now we know that, happily enough, there are many microscopic paths to the same macro quantity, and this quantity is called entropy of the macro state. The more microscopic avenues you have to the same macroscopic state means that this macroscopic state is very likely to be realized because there are many possibilities in macro world to get to the same macroscopic state. This is the end. And when I say this computational physics is an art of cheating, it is an art of cheating, but cheating in an honest way, which means that you want to choose the best path from here to here. Best means least CPU time, right? Very practical. So the path which is the minimal amount of computational work, but you have to choose something which is still compatible with the basic physics, otherwise you'll go rubbish. Okay? So when you derive the Lattice Boltzmann along this way, along statistical mechanics, the people who developed in the early days, those who wrote the Lattice Boltzmann without using it, did the right job. They put the microscopic world, they chose the lattice gas dynamic, which is just that one very, say that this path is very windy, and they took the straight path, because in the lattice, things are much simpler. But they made sure that this path has all the nice properties, energy conservation, and second principle. Second principle, well, some of you might be aware of the H theorem in kinetic theory, but all of you know the second principle of thermodynamics, which is to say entropy, if I have a change of state at equilibrium, I can entropy, well, I would say in a dynamic form, if I go from a non-equilibrium state here to an equilibrium state like this, a typical example with temperature, if I have a hot body and a cold body, at equilibrium they go to the same temperature, so there is a quantity which is only increasing, and at equilibrium it stops increasing, okay. and it settles down. This evolutionary constraint, the second principle, has to be fulfilled. Okay. And in the language of kinetic theory, this is called H theorem. I will not bother with you after the break. So, as I said, the lattice gas took a path which was very smart, very straight, and much less computationally intensive than the Newtonian gas. Zanetti and McNamara, with their lattice Boltzmann, instead of starting from here, they reconnected here. There would be something useful to compute, because they removed the problem of the statistical noise, as I told you. Higuera and Jimenez worked out a collision operator which is much less expensive than the Boltzmann collision operator, but still it was along this line. When we did this, we broke that. And in principle, we lost the H theorem, and we lost the second principle. The lucky strike is that you don't see that until you go to very, very, very low viscosity. Okay? That was the lucky strike, and I don't see any reason why it should have been like that. To me, it's just a lucky strike. But just to say that doing things top down was smart, very effective, but there was some red lamp, and we didn't realize that at all until Lydia came. And in fact, the entropic method is a way of restoring this second principle and showing you when you have it and when you don't, and that explains why sometimes you are stable, sometimes you are not. So, should I stop here before
Yeah, just 5 minutes.
I take some, I would like to take questions, just in case. Everything is clear at this point.